ladies and gentlemen, today's class recording has started. So, over the past couple of days, we've been drawing and discussing orbital diagrams. Give me a description of what an orbital diagram is. Or what does an orbital diagram do for us? Joanna, go ahead. How about it shows us how the electrons are distributed? So it doesn't necessarily distribute them for us, but it shows us how they are distributed, right? So, 3 rules that we use when determining where these electrons go and how they are distributed. Rule number 1, first and most important rule, is the off-bow principle. What does the off-bow principle tell us? Orbitals are filled from lowest energy to highest energy, and that means which ones are we filling first?
1s.
Closest to the nucleus, which is always 1s, all right? So, off-bow principle. Orbitals fill from low energy to high energy. Pauli exclusion principle. What does the Pauli exclusion principle tell us? Or what does it do for us as far as orbital diagrams are concerned? Jack, go ahead.
Each orbital can only hold 2 electrons.
Each orbital can only hold 2 electrons, and we have to distinguish them from each other, right? And then yesterday we talked about Hund's rule. What does Hund's rule tell us? Christina, go ahead. You have to distribute electrons evenly. That's a good start. Between, and let's finish that, because which orbitals are we distributing electrons evenly between? Got some help? Eric, go ahead. Orbitals of the same energy, let's go with energy, right? So, right, when we look at this diagram that shows us all the different orbitals and all the different energies, when we come across situations like this, where we have multiple orbitals of the same energy, we have to distribute those electrons evenly among them. Okay? Good there. All right. Before we move on to electron configurations, I want to make a jump back to, or try to make a connection back to the stuff that we did over the past couple days with the quantum numbers and the picture and stuff like that. So, sorry, if you would like to pull out your outline with the quantum numbers, it might be helpful for the exercise I'm going to have you do here in just a second. So, pull out your old outline, the one that has the big complex picture on it, and then it has the quantum numbers on it. All right? All right. So, here is a picture of the orbital diagram for oxygen, which I believe we drew at the bottom of page 2 on the current outline that we're working on. Yes?
Yep.
All right. Let's take this electron. Okay? That electron right there. Talk to the person next to you and come up with a set of quantum numbers that describes that electron that I highlighted right there. Okay? Talk to the person next to you. Come up with a set of quantum numbers that describes that electron that I just highlighted on the board. Go.
It's just negative 1/2 or positive 1/2. It doesn't matter which number. So, 0, wait, what's S again? Spin number. Is the x-axis right to 0? So what happens if, Oh yeah, 1/2 or negative. Oh, like that. So what is it? That would be that was
All right. So, bottom left-hand corner right there. Okay. First, I'll ask you this question, okay? Do we understand where those 4 numbers came from? If you don't, raise your hand and let's talk. Don't be a chicken if you don't understand where they came from.
Yeah, don't be a chicken.
Okay. Question number 2. Is that the right answer?
It doesn't matter.
That is a right answer, okay? But it's not necessarily the right answer, right? There's one other possibility that we could change here, yes?
Yep.
What could we change on this drawing? Or on this set of quantum numbers? Oh, good.
S could be negative 1/2.
S could be negative 1/2, right? If we're only talking about one electron, we don't exactly know which one's plus 1/2 and which one's minus 1/2 until we start comparing them to each other. All right? Good with that? Okay. Let's go to sodium. Okay? Here, I'm going to ask you about this electron.
That electron.
And I'm going to ask you about this electron. Talk to the person next to you. Quantum numbers for those two electrons. Go.
N for both of them is 2. L 0.
Yes.
M is to be negative 1. And then S will be negative 1/2 and positive 1. But they can be the same, but they can't be the same. So it could be negative 1/2 and negative 1/2.
And then it's negative 1/2, and it could be negative 1/2. They can be the same.
Yeah, because it's
Close, Frank. Close.
Different like
Not
shells.
correct. Those are not correct.
What?
Can you look at mine?
We'll get it.
Alright.
All right, 10 more seconds, then we'll discuss.
How is that not correct?
I'm going to have you try and figure it out on your own.
Oh, maybe just.
All right, let's discuss. Okay. So, what do you know about both of these electrons that I highlighted?
Both in the second energy
They're
level.
both in the second energy level, okay? And that means that what has to be true about N for both of them? Got to be 2, and then this one has to be 2 as well. What else do you know about those two electrons?
Both p orbitals.
They're both in p orbitals, okay? And that means that L has to be 1 here, and then L has to be 1 here. Oop. Okay. Now we start deviating, all right?
Yeah, Frank, my God.
So, we know that there are 3 p orbitals, and we have to distinguish between those 3 p orbitals, all right? So, Frank, do you know what you did? Okay, so, Frank, what did you write for M for this first electron, okay? So, Frank wrote 1 for this first electron here, okay? But M for the other one has to be different, right?
Different axis.
So, what are you going to call this one, Chris?
0.
Okay, Chris is going to call this one 0. Okay?
Okay.
Is that the only possible value for that one?
No.
No, it could have also been what?
Negative
Could have been
1.
-1 as well. Okay? Alright? And then for the spin number, right? I'm going to fill in those two. Okay? Are those right?
Not necessarily.
They could be. They could be switched, all right? Could they both be plus 1/2?
Yes.
Technically, yes, all right? Because we just have to distinguish between the two electrons within an orbital, right? Why did I make one of them plus 1/2 and one of them minus 1/2? Yeah, one's facing down, one's facing up. I kind of did that on purpose so that to see if you guys would pick up on that, right? But technically, because they're not in the same orbital, we could call them both plus 1/2 if we wanted to. They only have to be different if we're talking about two electrons in the same orbital. Okay, right, good.
And why the M's?
The M's have to be different because 2p here, but this is a different 2p orbital, right? Remember, how many 2p orbitals are there? There's 3 of them. X-axis, y-axis, z-axis, right? And these 2 electrons that I highlighted are in different orbitals. One's on the x-axis, one's on the y-axis, for example. That's what this number tells you. Which of the p orbitals is that electron in? And that's why they have to be different, because they're in different orbitals. How's that? You okay with that?
That is nice.
That's pretty advanced, but you guys, it sounds like you guys did pretty well with it. So, okay. All right. With that being said, let's fast forward to the back page of your outline,
Okay.
and let's talk about
Which one?
electron. Oh, the current one that we were
Electron
electron configurations. Okay.
Oh, geez.
So, the orbital diagram that we have been drawing, the orbital diagrams that we have been drawing, are shorthand ways of representing that big complex picture with all the orbitals that we drew on Wednesday and Thursday and Friday of last week. Even though those orbitals exist, not always have electrons in them. So orbital diagrams simplifies that big drawing and say, okay, where are these electrons exactly? Okay? Electron configurations are a shorter hand way of representing that picture. So a shorthand way of representing the locations around the electrons in the nucleus. Orbital diagrams tell us which orbitals are actually filled. Electron configurations shorthand represent that. Okay? Not as much detail as your orbital diagrams, but a convenient way of representing patterns, and we'll see that here in just a second. Okay? All right. So let's go back. I know you have space on the back page. I'm going to write electron configurations on the same slides as I wrote orbital diagrams, okay, just to keep them together. You have some space on the back page, that's fine. If you want to write it next to the orbital diagrams, that's fine too, okay? All right, shorthand way. So 2 things that electron configurations tell us. They tell us which orbitals are filled and how many electrons are in each orbital, okay? So, electron configuration for hydrogen is going to look like this. We have to talk about which orbitals are filled. So which orbital is filled in a hydrogen atom?
1s.
1s. Okay? So we start off with just writing 1s like this, all right? Okay? No line, just 1s. And then we use superscripts to represent the number of electrons in that orbital. So we know that hydrogen has electrons in the 1s orbital, but how many electrons does hydrogen have in the 1s orbital? Just 1. So we use a little exponent, right, to represent the number of electrons. So the electron configuration for hydrogen is 1s1. Okay? The circle is just my emphasis. Usually we don't put the circle on here. Okay?
Is it 1s2?
So then, helium, right? We're putting electrons in the 1s orbital. But Chris, how many electrons are in the 1s orbital? 2. So we use the exponent to represent that. Okay? By the way, we say this as 1s2. It's not 1s squared. Okay? It's not a mathematical operation. It's a number of electrons in each orbital. Frank, go ahead.
So you write down like the orbital even if it's not completely full.
Even if it's not completely full, because that is where electrons are, we just may not have filled up that orbital, right? So electron configurations have to tell us which orbitals have electrons in them and how many electrons are in each of those orbitals. Okay? All right, next, lithium. So we start off, right? What's the first orbital that has electrons in it?
1s.
1s. So, 1s, and then how many electrons are in that 1s orbital? 2. But that's not enough electrons, right? We also have 1 left to go, or 1 more to place. So what's the next orbital that shows up?
2s.
2s. So we write 2s. And then how many electrons are in that orbital?
1.
Just 1.
IS2.
1s2, 2s1. Okay?
Basically just something different like that.
Yep.
Are you gonna ask us like all the orbital diagrams too?
Yep.
Are you gonna ask us
And
like,
you need to know the difference between an orbital diagram and an electron configuration. Okay? So if I ask you to draw an orbital diagram and you write this for me,
Oh.
wrong.
is there a diameter like the one above it?
This is the orbital diagram.
That's, okay.
This is the orbital diagram. This is the electron configuration.
Okay.
All right. Boron.
ES.
1s2. 2s2.
Now
Well, what's the next orbital that's filled?
3-2p.
Okay, so when we were doing orbital diagrams, right, we drew all three of those p orbitals because they all had the same energy. Electron configurations, shorthand, okay? When we have multiple orbitals that have the same energy, in an electron configuration, we don't show them separately. So in this case here, we're just going to write 2p, and then how many total electrons are in 2p orbitals at this point in time? Just one.
Carbon is.
Okay? That's fine. Now let's talk about carbon. Okay? So, 1s2, 2s2, then 2p, but we don't distinguish between them, so we just go 2p2. Okay?
I told you. You said 2p.
Now, looking at carbon, right? The electron configuration doesn't show us as much detail, right? What two rules of orbital filling does the electron configuration not really show us about? Eric, what's one? Okay, we're not showing Hund's rule here, okay? 2p2 is not identifying that those electrons go in two different orbitals within the p sublevel. You need to know that, right? It's a shorthand way. It's not as detailed, but it does represent it. What other rule does electron configuration not really show us? Off-belt principle still is kind of in effect because we're filling up orbitals in the right order. But what other rule is it not showing us?
Oh my god.
Pauli exclusion principle. Pauli exclusion principle tells us each orbital can hold how many electrons? 2, but what do we have to show about those 2 electrons? That's Hund's rule. What about the 2 electrons in a specific orbital? What about the 2 electrons that are in the 1s orbital here? What is this electron configuration not showing you? It's not showing you what? That they're different. It's not showing you one up, one down, right? Again, you need to know that. Like that's part of Pauli exclusion principle. Electron configuration doesn't give you that much detail, but it's still there. All right? Good? We okay with that? All right. Next electron configuration on your outline is actually one that we didn't draw an orbital diagram for, but that's okay. All right. So let's go here. Nitrogen. Okay. We look on the periodic table and we find that nitrogen has how many electrons? 7. 7 electrons for nitrogen. Okay. I don't have the chart here, but so Eric, off-belt principle still holds, right? So what's the first orbital that gets filled up? 1s is always the first orbital. So if we're going to write an electron configuration for nitrogen, it's always going to start with 1s, right? How many electrons in that 1s orbital? 2. Okay. Next orbital that gets filled up? 2s. So 2s, 2, because it can hold there, right? Then the next set of orbitals we go to is 2p. And then how many electrons are in those p orbitals? 3. What does this diagram not show you? Or what does this electron
How they're
configuration not show
distributed.
you?
How they're distributed.
How they're distributed. If we have 3 electrons in the 2p level, or sublevel I should say, what do we know about those 3 electrons?
One are in each.
1 in X, 1 in Y, 1 in Z. The electron configuration doesn't show that, right? But it's still the case. All right, good there. Okay with that? Eric, go ahead. Take a couple if you need. All right, neon. 1s2, 2s2, 2p6. Okay with that for neon? Does that make sense? Okay. All right. Then for sodium, okay, I already made some notes here, but
Whoa.
blue, right? 1s2, 2s2, 2p6, 3s1.
This is way easier.
Does that make sense? Where I got that from? Where I got that electron configuration from? Is that okay?
What's the syphilis?
Now, even though this is shorter than doing an orbital diagram, we're still starting to get a decent number of pieces here. So, the noble gas configuration that we used to shorten our orbital diagrams, we can also use to shorten our electron configurations. Right? This blue box, we said, was the same for sodium as it is for neon. Those 2 blue boxes, right? The first part of sodium's electron configuration and the beginning part of neon's electron configuration, again, are exactly the same. Yes?
Yes.
So we can shorten our orbital or our electron configurations the same way we did with our orbital diagrams.
For a Tesla, POQ will be up there.
Yeah, but you will. There you go. You get one of these. You don't have to look at it upside down. You can look at it right later. But yeah, you will all get one of these. It's laminated.
That's nice.
But it also like you'll get it at the beginning of the test, and you'll give it back to me at the end of the test. So like you can't write on it and stuff like that. So there you go. If you want to use it, you can use it. All right, good there. You all right with that? Let's do this. Give me electron configuration for potassium. Write me the full electron configuration for potassium, and then write me the noble gas configuration for potassium.
That's a long one.
Write me the full electron configuration, and then also the noble gas configuration for potassium.
Yeah, Frank.
You're good. There you go.
You to read the whole thing first. Oh, that's what he said.
Oh my god.
Alright. So there's my full electron configuration. Okay. Does that make sense? Good where that came from? But then up till here, right? Joe? Up till there, that's which element? Argon. That's argon, right? That's 18 electrons. So we can shorten this up, put argon in brackets, and this put the 4s1 on the side. Okay. All right. To wrap this up, why don't you do the last two that are on your outline? Letter L and letter M. Letter L and letter M.
C police.
We have to do both. Should we do both?
Yeah. No, you can do noble gas if you want to. If you understand how to do the noble gas right off the bat, go for it.
Wait, what I do?
Because then we start the next row, we start the next energy level. Okay, so you can't just jump in the middle like that would so difficult.
Can you check when?
I'll put them up on the board. Chill.
That's manganese. Oh, arsenic is 33.
Everyone good with manganese? Have you done manganese? Check manganese up on the board. Either one of those counts. Either one of those counts. All right, good. And then either way, yeah, either way is fine.
Have fun on reading.
Hashtag P says that. Frog Della on 3. 1, 2, 3, Frog Della. Della quit.
He did? No, he didn't quit.
They did.
He's dead. No, he didn't. His dad
Oh,
took
told
him.
me.
Yeah, this is on recording, just so you know. All right. How do we do on arsenic? Okay there, right? We used the chart a little bit farther than we had before, right? If we look at the 3D, the next one we run into moving upward is 4P. So we go back from 3D back to 4P. Okay. Good? Timmy, good. Chart is going to be on the test, yes. So you will have, Sammy, you'll have the periodic table, and then the chart is reference material on the test. So you will have that, yes.
The lanthanoids and the actinoids.
All right, how we do? Okay? Feel comfortable?
Yeah.
All right. Let's not worry about that last part down at the bottom. Roman numeral number 6. We will get into that more in the next unit when we start talking about properties of different atoms and what they do and how they behave and stuff like that. For now, let's cut it off there at electron configurations. Okay. So tomorrow you have time in class to do problems on the book, work on the objective sheet, ask me questions, whatever you need to do to prepare for your test on Friday. All right. Good job today, everybody.